All known terrestrial biological systems exist on a fragile, rigid veneer that represents less than 1% of the Earth's radius. Beneath this thin crust lies a massive thermodynamic engine. When tectonic plates fracture and subduct, the rock dives into the mantle, a dynamic, convecting mass driving the surface geology of our planet. This 1D radial model illustrates the scale of that engine. The mantle constitutes approximately 40 to 45% of the Earth's total volume. It is not a static monolith, but a moving mass that transfers heat from the deep interior to the surface. To project how this internal flow drives tectonic plates, geodynamicists use mantle circulation models, or MCMs. These high-resolution 3D spherical algorithms use conservation equations for mass, momentum, and energy to simulate thermal currents rising from the core. These thermal currents don't just move plates horizontally. They induce non-isostatic vertical motions at the Earth's surface, a phenomenon called dynamic topography. As heat rises and falls, the crust warps, dictating the formation of sedimentary basins and massive paleoclimatic fluctuations over millions of years. But these sophisticated models face a critical limitation. They are primarily theoretical. Geodynamicists are mathematically projecting the behavior of an engine that no human has ever observed through direct in situ sampling. Because direct observation hasn't been possible, researchers rely on seismic tomography, interpreting acoustic waves passing through the rock. These indirect inferences carry deep uncertainties regarding the hydration states and precise chemical composition of the deep lithosphere. This cross-section highlights the specific layer where acoustic wave velocities abruptly change. This is the Mohorovičić discontinuity, or the Moho, the exact boundary separating the crust from the higher density, more ductile peridotite of the uppermost solid mantle. The acoustic data here is so ambiguous that researchers often have to manually add chemical density anomalies into their models just to make the mathematical equations correlate with observed topography. To eliminate these assumptions, we need empirical ground truthing. We must physically penetrate the Moho, extract mantle peridotite, and calibrate these global geodynamic models with physical evidence of heat flow, stress, and permeability. Reaching the Moho requires managing the compounding physics of ultra-deep drilling, an effort that has evolved through 3 distinct technological generations. This dimensional comparison illustrates the immediate geographical problem. Beneath landmasses, the continental crust extends downward 35 to 70 kilometers. Beneath the ocean basins, the crust is thin, typically ranging from only 5 to 10 kilometers. Mathematically, the deep ocean basin provides a massive shortcut. If the goal is to reach the mantle, starting on the seafloor eliminates tens of kilometers of solid rock from the mission profile. This logic sparked the 1961 initiative, Project Mohole, aiming to bypass the continental crust entirely and drill straight through the oceanic basement to the Moho. Doing this introduced a massive mechanical constraint. Traditional offshore drilling was confined to shallow waters, where rigs could be tethered to the seabed. In the open ocean, the weight of a kilometers-long untethered drill string would snap under the rotational forces of the drill and unpredictable currents. The engineers solved this by inventing acoustic dynamic positioning. They equipped the drilling barge with motors linked to a continuous acoustic feedback loop from transponders moored to the seafloor. This system actively counteracted environmental forces, holding the vessel precisely within a 180-meter radius. Operating in waters 3,600 meters deep off the coast of Mexico, the expedition successfully bored 183 meters beneath the seafloor. The final 13 meters of the extracted core consisted of solid basalt. For the first time, a drill penetrated through the sedimentary layers of the ocean floor and into the volcanic oceanic basement, providing physical confirmation of density properties derived from seismic studies. Project Mohole proved that drilling toward the mantle was mechanically possible. But the logistical vulnerability and the immense costs of deep ocean operations eventually forced the next generation of engineers to seek the mantle on dry land. In 1970, the Soviet Union adopted a brute force onshore strategy. Located in the frozen Baltic Shield, the Kola Superdeep Borehole, designated SG3, was an attempt to penetrate 15 kilometers deep into ancient, stable continental crust. The mechanical friction of this approach was immense. Standard rotary drilling, where a surface mechanism turns the entire drill string, becomes impossible at extreme depths. The torsional friction and mass of several kilometers of steel pipe would simply overwhelm the rig. To bypass this, Soviet engineers perfected the downhole mud motor. The main drill pipe remains stationary, while highly pressurized drilling mud is pumped down the shaft to power a turbine located directly above the drill bit. This causes only the bit itself to spin, drastically reducing the torsional stress on the drill string. This solved the friction problem, but it introduced the metric that dictates all deep earth exploration: the geothermal gradient. Predictive models estimated that temperatures at 15 kilometers down would be approximately 100 degrees Celsius. As the drill descended, the actual geothermal gradient scaled at nearly double the expected rate, skyrocketing to 200 degrees Celsius at 12,262 meters. At these temperatures and pressures, the mechanical properties of the Archean granite changed. The rock ceased to behave as a brittle solid and began to act plastically, oozing back into the wellbore faster than it could be extracted. This triggered a cascade of equipment failures. Fluids under supercritical conditions boiled. Cooling circulation became impossible. Drill bits melted in the heat. Though they reached less than a third of the way through the crust, the data extracted upended geological assumptions. At 7 kilometers down, the drill encountered no basalt, disproving the predicted Conrad discontinuity and proving the continental crust is composed entirely of granitic material. Even more unexpected, the project extracted intact microfossils from 6.7 kilometers down. These 2-billion-year-old structures survived the hostile thermodynamics, encased in organic carbon and nitrogen compounds that acted as pressure vessels miles beneath the surface. The Kola project proved that the ultimate barrier to the mantle is not mechanical force. It is a thermal wall that changes the physical properties of rock and fluid, demanding a new class of engineering materials to survive the heat. Ultra-deep terrestrial drilling languished for nearly 30 years. That changed in 2023 with China's Shendi Take-1 well, a multi-billion-dollar project located in the Tarim Basin of the Xinjiang region. Utilizing a 12,000-meter automated drilling rig, this project pushed the tracking metrics into new extremes. Shendi Take-1 reached an ultimate vertical depth of 10,910 meters, encountering bottom hole temperatures exceeding 210 degrees Celsius and hydrostatic pressures surpassing 145 megapascals. Operating in these high-pressure, high-temperature environments causes severe abnormal pore pressure gradients. The risk of formation fluid influx and catastrophic blowouts scales with every meter dropped. At these depths, components suffer from multi-field coupling stress. Simulations show structural damage at the casing cement sheet interface increases by approximately 40% as the elastic modulus of the cement increases from 3 to 15 gigapascals, and the Poisson's ratio climbs from 0.22 to 0.34. To prevent catastrophic degradation, modern components must be fabricated from advanced alloys, including nickel-based superalloys. These are paired with high-temperature drilling muds that act as a hydrostatic counterpressure to the plasticizing rock. But hardware is only half the solution. At 11 kilometers deep, thermodynamic fluid shifts can happen instantly. Human reaction time is too slow to manage the variables required to maintain borehole stability. Modern rigs use a closed-loop architecture. The WITS-ML protocol ingests drill string data directly into a central AI node. This agent instantly computes parameters like mechanical specific energy. If an anomaly is detected, it autonomously adjusts the bit's weight and rotary speed to prevent failure. This autonomous perception happens in fractions of a second, preventing the drill string from twisting off or fluid shifts from triggering a blowout. Simultaneously, a geological steering agent uses real-time logging data to dynamically construct models of deep earth fault systems, navigating the bit trajectory through complex rock layers. This precision allowed Shendi Take-1 to secure natural gas at depths of nearly 11 kilometers, proving that viable hydrocarbon systems exist far deeper than traditional thermal destruction models allowed. Shendi Take-1 illustrates that surviving extreme depth relies on digital systems capable of processing variables faster than human reaction time allows, managing the multi-field coupling that destroyed earlier attempts. While Shendi proved the viability of an 11-kilometer system, the 35-kilometer thickness of the continental crust means no terrestrial rig will ever reach the mantle. To bridge the final gap, science must return to the ocean floor. The Mohole to Mantle, or M2M initiative, proposes combining the oceanic shortcut of Project Mohole with the AI and superalloy advancements of the current century. The scientific objective is to drill through an intact section of fast-spread oceanic crust and penetrate 500 meters into the lithosphere to capture the first sampling of unaltered mantle periddotites. Extracting these samples will illuminate the mechanics of the deep carbon cycle, the nature of hydrothermal cooling processes, and the precise chemical composition of the convecting mantle. Piercing the Moho requires finding a specific thermodynamic Goldilocks zone in the ocean to avoid the thermal wall that halted the Kola project. Selecting this site involves a rigorous matrix of 5 geological prerequisites. First, the crust must have formed at a fast-spreading ridge, greater than 60 millimeters a year, to ensure structural uniformity. Second, it must be ultra-thin, with a total crustal thickness of under 6 kilometers. Third, the lithosphere must be thermally aged over 15 million years. Older crust supports a lower geothermal gradient, ensuring the temperature at the Moho interface remains below the 250 degrees Celsius limit of drilling equipment. Finally, the site must exhibit distinct sub-Moho seismic refractions and specific mantle anisotropy. This allows geodynamicists to contextualize the samples and understand the directional flow of the Mantle engine. The effort to pierce the Earth's crust has evolved from untethered barges and melting steel to the precision of AI-steered oceanic super rigs. Reaching the mantle is no longer an exercise in blind mechanical force. It is the ultimate optimization problem, balancing thermal physics and digital control to empirically ground truth the engine of our planet.